Welcome to lecture number 34. This is on pump characteristics curves. In the previous lecture, we have been talking about centrifugal pumps and the principle, right. So, and also how to calculate the head. So, once you know the head and using the discharge, you can estimate the pump the power required to lift the amount of water from a water source, both in when the water source is below the central line of the pump and when the water source is above the central line of the pump. In both cases, we have seen few examples in the previous lecture. So, now so what exactly the characteristic curves of a particular pump? Just like we human beings, our characters are different. So, the pump which is manufactured by a manufacturer A is different from the pump with the same principle which is manufactured by the other manufacturer. So, definitely we need to study the pump characteristics. This will be useful in selecting an appropriate pump for your desired application. Sorry. So, here so before going to the pump characteristic curves, so there is a concept called the cavitation. So, this is a common problem in centrifugal pump, because the cavitation itself indicates the formation of cavities inside the impeller. So, how this is going to form inside the impeller? So, what happens when when the impeller rotates, right? So, when the speed increases, obviously, so that will increases the fluid temperature. So, when the fluid temperature increases, so there is the vapor pressure, the water particles and the water molecules started escape from the surface, right. So, then the because of vaporization. So, then all these vaporized particles which are accumulated inside the eye of at the eye of the impeller, then so those are called really the cavities. Okay. So, when the cavities passes from the low pressure which is at the eye of the impeller and to the high pressure at the end of the impeller, so or the end of the vanes. So, all the bubbles which are formed at the center of the impeller are going to burst. Okay. So, this mechanism or this phenomena is called cavitation. So, due to that, so what is the implication of that process? So, the implication clearly you can see here this is due to cavitation. So, this is for example, an impeller. So, due to the cavitation, so the impeller edges are going to wear. Okay. So, there is a chipping of an impeller surfaces or the wearing of impeller surface, right, when completely it is going to damage the impeller. So, so this clearly shows how the cavitation is going to form at the center of an impeller. So, when the impeller rotates at high speed, so that causes the increasing the temperature of the fluid, and then that causes the vaporization of the fluid, and all vaporized particles formed cavity. So, then when the cavity transports from low pressure to high pressure, it is going to burst, and you can see the bursting effect here. So, mostly at the edges. Okay. So, this is an important aspect we need to study, and then so the next is so again the cavitation, how to indicate the cavitation. So, basically the cavitation coefficient is defined as HSV, which is net positive suction head. We are going to see this in the next slide, but what exactly the net positive suction head is. So, in centrifugal pump, if you see the suction, suction line, there is a footwall, right. If this is the pump, okay, this is the pump. So, so at the footwall, so in order to lift water from this point to the and to the center of the impeller, right. So, you need to maintain, or you need to have a minimum suction. Okay. So, that suction is required to lift water from this to this one. So, the net positive suction head is the minimum pressure or the negative pressure required to lift water from the source in centrifugal pump. So, that is called net positive suction head. So, this is net positive suction head divided by the total head is the cavitation coefficient. So, here if you see, so the cavitation coefficient, which is the critical value at which cavitation will begin, can be determined by testing the pump at constant speed and capacity at varying suction lifts. So, maintain the constant speed at varying suction lifts. You can find out at the critical suction lift for which you can lift water basically, and that is the critical value in case of cavitation, I mean in case of centrifugal pump. And the efficiency increases for lower I mean these sigma values. So, if the cavitation coefficient is greater than 0.3, then that is the pump is operating successfully. So, then the safe suction lift, it will be like 4.5 to 5 meter for most of the pumps. So, in this picture it is clearly shows. So, if you have the suction, right, and eye of an impeller and the discharge point of impeller. So, here the suction point, eye point and the discharge point. If you see the pressures, right. So, the pressures are in the suction point. So, this is the pressure, right, and then in the eye of impeller the pressure is going to decrease, right, the low pressure, and then the discharge point the pressure is going to increase, the discharge point. So, here this the low pressure which is at eye of an impeller, if it is less than the vapor pressure of the fluid, then there is a problem with the cavitation. The cavitation is going to form, or cavitation in the sense the bubbles are going to form. Here in the first case, the low pressure at the eye of an impeller is above the vapor pressure of the water, and no bubble is going to form and no cavitation is going to take place, whereas in this condition the cavitation is going to take place. So, then the net positive suction head, just we introduced in the previous slide, it is the positive, this is the head needed to pump inlet, may be termed as the net positive suction head or net required inlet head. So, the total net positive suction head will be equal to net positive suction head and entrance and other frictional losses in suction pipe. Okay. So, and then when pumping water level is below the pump inlet, suppose you have pumping water level which is below the inlet of on the central line of the pump, right. So, then net positive suction head is equal to atmospheric head minus the HSS. So, pump water level is below the pump inlet. So, pumping water level which is below the central line of the pump. So, in this case the net positive suction head which is equal to atmospheric head minus the static suction head. This is called static suction head, or I mean total static suction head. So, and then when pump water level, right, is above the pump inlet. So, suppose in this case what happens. So, you have water level is here and you are pumping it to top. Okay. So, in this case the net positive suction head is equal to atmospheric head plus HSS. So, that is static suction head. So, then pump characteristic curves. So, these are the curves, the simple graphical representation of the behavior of a particular pump. Generally it is represented with discharge on x axis, this is the Q on x axis, and y axis H, that is head, okay. And then the other parameters here, this is the power BHP on y axis and efficiency, okay. So, these curves, so here we are showing the three curves or three characteristic curves of a particular pump, which has Q versus H and Q versus power P and Q versus efficiency, okay. So, for a particular pump, these characteristics curves are are different from one pump to another pump. So, the usefulness of this particular curve is, so when you go to a manufacturer or when you go to purchase a pump in a shop. So, you have to check the pump characteristic curve, and you can see whether the discharge you are expecting and head you are looking can be really obtained from the particular pump or not. So, if you want, so here, so this is the head and discharge curve, for example, and so your desired discharge is like suppose 16 LPS, right, and that can, this particular pump can have for this particular discharge around 29 meter head max, and then the corresponding. So, this is the one, and then the same thing you can extend on the line is extending on the other two curves. So, this will give the power required, and this will give the efficiency of the particular pump, okay. And then so the next is, so what happened to the characteristic curves when you have connected the pumps in series and connecting the pumps in parallel. So, here in this example, this is the pump number 1 and pump number 2. So, these two pumps are connected in series. So, in series when you connect, so the Q, the effective or the final discharge will be same when you connect the two centrifugal pumps in series, but the head is going to increase. So, added up. So, head due to this pump and head due to this pump. So, and then so with the same discharge you can increase the head when you connect two centrifugal pumps in series, okay. So, here and then the combining efficiency, the E series is equal to Q into the combined head divided by the BHP of 1 and BHP of 2, pump 1 power, pump 2 power, and multiplied by 102. So, this will give the combined efficiency of the pumps which are connected in series. So, then you are expecting more discharge, rather you are not interested in the head. So, in that case, so the pumps are required to connect in parallel. So, let us see the next slide. So, when the pumps are connected in parallel, so here, so the heads are same, right. So, here pump number 1, pump number 2. So, these pumps are connected in parallel. So, this is Q which is going in, Q this is Q 1 plus Q 2 will be coming out, right. So, then the powers anyway you have to add it up, and then H will be same head, the only the Q is going to increase by individual discharges. So, the combined efficiency in this case, so since H is not changing, H multiplied by the effective or the total Q, and then 102 and BHP 1, BHP 2, this will give the efficiency of the pumping system. So, when in which the pumps are connected in parallel. So, then pump performance, so basically it depends on the design and installation. So, these two, so design and installation definitely influences the performance. So, installation is I mean this is basically the practical influence, and the design part. So, the design part we need to consider the design parameters such as the diameter of the impeller and the speed, the power, head, discharge, all these parameters, and we need to understand how these are connected, how these are having relationships among themselves. So, let us see. So, in this, so this can be really studied by using the affinity laws. So, the affinity laws basically it says the standard expressions, so that define changes in pump capacity, head and BHP, that is the power, when change in made in pump speed and diameter. So, here the capacity, the discharge is a function of D and N, this is one, and H is a function of D and N, and P is a function of D or N. Okay. So, these laws are called affinity laws. So, the advantage of these laws is, so you bought a pump, right, and then the manufacturer's designed diameter of the impeller and designed the RPM, right, and the corresponding the values Q, H, P, and you want to change the speed, or you want to change the diameter of the impeller, and how these parameters are influencing with the change in diameter and change in speed. So, that is basically the affinity laws will give a good information. So, here if you see the affinity laws, for example, the speed. So, the effect of change in pump speed on pump performance. So, the relationships are Q is equal to Q 1 into N by N 1. So, this is linearly related, and but in this is the square, right. H is equal to H 1 into N by N 1 square, and P is equal to P 1 N by N 1 power cube. So, that means Q by Q 1 is equal to N by N 1, and H by H 1 is equal to N by N 1 square, and P by P 1 is equal to N by N 1 cube. So, this simply you can remember this. So, here where N is the N 1 is the speed at which characteristics are known, right. N is the desired new speed, and Q 1 pump capacity at N 1 and Q pump capacity at N RPM, P 1 BHP at N 1, H 1 and Q 1 and P BHP at N H Q. So, all these things. So, knowing the parameters, how to estimate the other parameters for a particular change. So, that is the affinity laws. So, and similarly in case of diameter, right, changing the diameter. So, Q 1 or Q by Q 1, let us say Q by Q 1, which is equal to D 1 by D by D 1. So, Q by Q 1 is equal to D by D 1, just like in case of in speed, that is Q by Q 1 is equal to N by N 1, and Q by Q 1 I am sorry, and then the next one is H by H 1 is equal to D by D 1 square, similar to N by N 1, and P by P 1 is equal to D by D 1 cube. This is also similar to N by N 1 cube. Okay. So, this is the change in diameter. So, what if both diameter and speed changes? So, that will, this is the equation when you have change in diameter as well as change in speed. So, the capacity can be estimated by knowing the Q 1, D 1, N 1. Okay. So, then how do we get these equations? This is very simple. So, you take the two. So, Q by Q 1 is equal to N by N 1, right, and another equation Q by Q 1 is equal to D by D 1, right. So, then multiply these two. then you get q by q1 square is equal to n by n1 into d by d1. Okay. Now, q by q1 is equal to the square root of n by n into d divided by n1 into d1, and then q1 goes here and you get q is equal to q1 into square root of n1. So, if you have both changes. Okay, so this as an example, if you know the the diameter and other parameters from the and then you can estimate what are the parameters corresponding to the change in impeller diameter. So, here impeller for particular impeller diameter and particular speed, right. So, let us say this is d1 and n1. So, we know this q1 or since it is already written. So, this is a q, h, p and this is d and this is n. So, knowing this you can estimate q1, h1, p1, d1, n1. So, here the question number 1 is determine the pump output for 9-inch impeller, that is d1 is given. For d1 what will be the capacity and head and all of this stuff. So, you can use the affinity laws. So, knowing the so for example, your case sorry. So, for example, so we know that q by q1 is equal to d by d1, right. So, q is given, d is given, and what is q1 for d1? So, d1 is 9-inch and this is 13-inch, right, and this one is 800 GPM. So, this is simple math, you can calculate q1. So, that is determine the pump output, and similarly you can so once you know q1, right, q by q1 and d by d1, you can calculate the other parameters like h by h1 is equal to d by d1 square, like similarly p by p1 is equal to d by d1 cube. So, here look at this. So, the parts power, the p is given, you can correspondingly you can calculate p1, and h is given, you can correspondingly calculate h1, right. And then you can also use, if you have a characteristic curve graph, right, you can definitely use this graph by knowing the diameter, right, 13-inch diameter, and this probably you get the 9-inch diameter. Okay. So, and the second question is calculate the corresponding reduced speed. Yeah, similar when you get the new speed, right, for the reducing the diameter to 9-inch, right, you calculate the speed and you can get the reduced speed using the equations. Okay, so, we have other pumps, whatever we covered is the centrifugal pump, and we also have other pumps like propeller pumps. So, which is being operated, or the main principle here is, so you might have seen the propellers in case of boats or in case of the aeroplanes. So, those are propellers. So, you clearly see, so the propeller takes the air inside, okay, takes the air inside. So, it guides the air inside just like this. Okay. So, so similarly here, so these pumps basically works on the same principle. So, for high discharge and low head pumping, so you get more discharge, but low heads, and is suitable to lift water from canals, rivers and streams, right, because all our surface waters you can easily use propeller pumps to remove to lift water, and very popular in rice growing regions of Southeast Asia. So, this is because the rice requires the shallow water. So, that will be very useful, and the pressure head is developed mostly by the propelling or lifting action of the propeller blades on water. Okay. So, assembly will have like a propeller and diffuser assembly. So, here So, this is a propeller and diffusion assembly is here, okay, and the pump column. So, this is the pump column and this is the discharge column, and the pump drive is, this is the pump drive. Okay. So, these are the basic or main equations, main parts in propeller pumps. So, if you see this propeller, what happens? So, the water which is due to the propeller action will be the water will be taken inside of the propeller, and that will be guided through the discharge column, and then finally it will lead to the discharge column. Okay. And so, the next pump, the mixed flow pump. So, mixed flow is, it has both the propeller action as well as the centrifugal action. Okay. So, the combination of some of the features of both vertical turbine pump, that is centrifugal pump, and propeller pump. Okay. So, both is going to, if you see here, so this is a propeller. So, first water will flow through the impeller, right. So, this is the propeller, then impeller. Okay. So, then it guides. Okay. So, the propeller it goes straight, then after that it goes radial. Okay. So, radially it goes. So, applicable for high discharge medium head like 2.5 to 10 meter it can be used, and extensively used for drainage pumping, right, and also from canals and rivers. So, the previous mixed and the propeller pumps and mixed flow pumps, so it gets more head than the propeller pumps because of this centrifugal action which is added in this pump. So, head is developed partly by centrifugal force because the the impeller, and partly by lift vanes on the liquid. Okay. So, flow enters axially and discharges in axial and radial direction, right. So, it likes comes axial and then radial and then this one. Okay. So, if you see this, it goes like this. Okay. And the main difference between the propeller and mixed flow pump is the construction of the impeller. So, which gives outward thrust to the water in addition to the imparting it on upward velocity. So, outward thrust. So, in not only in addition to imparting to upward velocity in case of centrifugal pump. So, there is an additional the principle is outward thrust. So, the next is a jet pump, or this is also called ejector pumps. So, this is basically the centrifugal pump, and which has the additional jet unit. Okay. If you see, so how this jet really works. So, the centrifugal pump, what happens? So, it's practically it is applicable up to 7.5 meters, something like that. If you want to have more head, so definitely you need to have a jet assembly. So, that will add the head more. Okay, that will add head to the centrifugal pump. So, how this jet works basically? So, here so this is inflow, right, inflow, but here the jet, there is a jet here and this is a throttle. So, because of this high jet, right. So, here the negative pressure is going to create, okay, because the high velocity of flow, negative flow. So, here anyway centrifugal pump which is sucking the water, but so that because of that here the water will anyway it is going in, but when you have jet assembly and this negative pressure, this added negative pressure which is created here, and that will definitely induce more inflow to the suction, right, compared to the regular centrifugal pumps. So, here the two types, shallow well jet pumps and deep well jet pumps. Those shallow well jet pumps are assembly which is inside the pump body. So, the jet assembly will be inside the pump body, whereas deep well, the jet assembly is inside the well, just like like a submersible. So, increases the suction lift from 6.5 to 8.5 meter in case of shallow well jet pump, whereas suction lift can go up to 50 meter or 90 meter in case of deep well jet pumps. So, efficiency is mainly influenced by nozzle and throat ratio, right, and then for the small jet. So, this is the nozzle diameter and this is the throat diameter, okay. And for the small jet pumps, throat is equal to nozzle diameter and the length of the throat. So, which is this one, the length of the throat, which is equal to 6 times the throat diameter, okay. So, these are the design parameters we need to consider. So, here same the jet pump, as I said, the two types, one is the shallow well jet pump and deep well jet pump. In the shallow well, the jet assembly, which is here, if you see this one is a throttle and this is a jet. So, this is inside the pump, okay. In the shallow case, this jet assembly is inside the pump, okay. So, what happens? So, this is the suction line in case of regular centrifugal pump, and then this is the impeller and the discharge. So, the jet assembly is here. So, because of and whatever the water which is inside the pump, so some part of water goes into the jet, right, and that creates low pressure here, and that induces more water from the suction, okay. And whereas the same same unit which is present inside the well, okay. This is the well, if you see, this is inside the well jet unit and this is the suction line, right, and this is the suction line, whereas this is additional water which is going into the jet, right, and here this is the throttle, right, and it is going to create a low pressure here, and that leads to extracting or sucking more water from the well, okay. And there is another special kind of pump is called Hydram or hydraulic ram, which is which works on the principle of a water hammer. So, water hammer is nothing but, suppose if you the flow is the fluid is flowing in a pipe or anywhere you might have seen, and suddenly if you make an impact on the flow, what happens? There is a receding wave, right. So, suddenly it impulses, so it creates impulse. So, that carry backwards, okay, that goes backwards, okay. So, that sudden impact, it is called hammering. We are really creating hammering force on the water flow, and that creates a ripple, and that ripple force can we can use to lift the water. So, how to use that, the particular mechanism in case of lifting water, you can see here. So, what this is basically this kind of pumps are being used in hilly areas where you do not require any electricity, okay. Hilly areas, lifting water from means low heights to high heights, okay. So, that is advantage with this pump, it does not require electricity, right. So, it have few parts, and if you see this water supply, mostly water supply in irrigation in case of hilly areas, the source of water may be a stream, a spring or irrigation canal, and simplicity of construction and automation operation of the hydraulic ram make it adopted in rural areas and works on the principle of this water hammer. So, here basically if this is the water source, right. So, so the water source goes, this is called a drive pipe, okay, and this is called a delivery pipe. So, you want to lift water from this to this, okay. So, this side to this side. So, this hydraulic ram, what happens? So, suddenly because of this slope, the water which is going to fall from this point to this point, and here there is a hydraulic ram, this is called hydraulic ram, right, or this is the box. So, in which So, because of the high velocity which is falling here, and all of a sudden, so here at this point, so suppose there is a high velocity which is falling and hitting this, right. So, when it hits this, that means you are obstructing the flow, right, and it recedes back, and since there is a chamber here. So, this is a chamber which is water is stored inside that, right. So, that water will be pushed up, and there is a valve that will be opens, and that opening of valve really leads to takes this water enter into the delivery pipe. Okay. So, similarly, so when the valve when the valve opens up, here pressure will be decreased, right, and then again that will push this thing back, right. So, then if this kind of the back and forth mechanism really helps in opening this valve, right, and leaving water here. So, this is a automatic mechanism, and no power is required, and only water will act as the energy source in this. So, here in the broader picture, if you see, so this is a water source which has this is a suction line, right. There is a valve here, okay. It is the waste water which is flowing from here, this is air chamber, okay, and then this is the delivery pipe, right. So, as I said, the main principle here. So, waste valve, there is a two valves here, the waste valve and there is a delivery valve, okay. There is a delivery valve. So, the waste valve and delivery valve, so these two valves are very important in functioning of the hydraulic ram. So, when the flow which is coming and hitting this valve, right, hitting this valve, because this high flow, and you are suddenly hammering it by obstructing the flow to the waste valve. So, what happens, because initially this will be opened, the waste valve pushes, so the water, some water will be wasted. So, that is called its waste valve, and then so because the spring action, so this valve again pushes the fluid into the system, the fluid to this towards this direction. So, when it pushes this, and definitely the escape point is this, because this is high high pressure, it anyway does not go. So, then this extra fluid which is going to lift the delivery valve, okay. So, then it goes into the air chamber, okay. So, then what when there is enough fluid, so air chamber, because of this air will be compressed, and that fluid goes into this, right, and when it is compressed, this will be closed. So, when this is closed, again the fluid is going to hit this one, okay. So, it is like hitting waste water waste valve, hitting waste valve, and then the same time opening the delivery valve, hitting closing, hitting the waste valve and opening the delivery valve. So, these two and also the compression. So, these things are really works on functioning of hydraulic ram. Yeah. So, the advantages are the simple in construction and operation, and does not require any this does not incur any running cost. It utilizes energy of water available freely, and no fuel or electricity is required, because this operates basically on hydraulic ram principle. It has only two moving parts, one is the waste valve, another one is delivery valve, as I said. So, both of which are lubricated by water itself, even it does not require any lubrication. So, it ensures continuous water supply as it operates throughout the day and night, does not cause any pollution. So, since it does not require any fuel to it, so pollution is not an issue, but only thing is, since it is continuously operated throughout the night, over day, and we need to arrange a storage tank in order to store the water, right. And then the limitations here are a minimum fall of 1 meter from the stream to ram is required, because that will really helps in creating that particular flow with high velocity flow. It lifts about 1/10 to 10/10 of the water supplied through the dry pipe. So, this is another disadvantage, like only 10 to 20% of water is being delivered out of 100 meter cube. Okay. So, since it works 24 hours a day, storage tank necessary, otherwise it is going to waste. Okay. So, with this I think the pump section is been completed. So, in this lecture we focused on cavitation and then pump characteristics. So, and then the other pumps like propeller pumps, mixed flow pumps, jet pumps, and then ram pump, which is entirely different from other pumps which does not require any electricity or any power and works completely on water hammer principle. So, the next lecture we are going to see some of the examples as tutorial. Yeah, thank you so much.